From International Journal of Heat and Mass Transfer, Elsevier. Flow and heat transfer characteristics of single jet impinging on protrusion surface. By D. Zhang, Huancheng, Jibing Lan, Jianhui Chen, and Yonghui Xie. Abstract. Combined PIV and numerical simulation. The flow characteristics of a single jet impinging on a protrusion surface were investigated, and the heat transfer characteristics were explored on the basis of numerical results. The flow structures of the single jet impinging on protrusion surface in different cases are similar. The jet flow impinges perpendicularly onto the protrusion and then turns its flow direction. Mini-flow separation occurs when the flow passes the edge of the protrusion and secondary impinging jet forms at the same time. The wall jet continues to develop along the radial direction after apart from the edge of the protrusion. Comparison with the case of smooth target surface shows that local Nusselt number increase occurs in the presence of protrusion. The local Nusselt number increases as protrusion relative depth increases. The average Nusselt number increases with protrusion relative depth and jet Reynolds number. For most of the cases, both heat transfer enhancement within the stagnation region and increase of heat transfer area result in overall heat transfer improvement of the jet impingement with protrusion target surface. Introduction. Impinging jet has been used in a large number of applications owing to its high rates of convective heat transfer in the stagnation zone. The practical use of impinging jet includes the cooling of gas turbine blades, combustion chamber, de-icing on aircraft, tempering of metal and glass, printing of circuit boards, cooling of microelectronic components, and drying of papers and textiles. As early as 1977, the correlation of impinging jet for engineering applications was derived by Martin based on the literatures of impinging jet. The numerical research on the laminar and turbulent impinging jet was overviewed by Polat et al. The parameters including single, array jet, circular, slit jet, vertical, inclined and stationary, moving target surface on the impinging jet were reviewed in detail. Polat et al. Noted that the implementation of two equation and algebraic stress turbulence models combined with the method of solving wall directly is most promising. Jambunathan et al. Summarized the single impinging jet experiments for the range of Reynolds numbers from 5,000 to 124,000 and the ratio of jet to plate spacing, h, and jet diameter, dj, from 1.2 to 16. The Nusselt number, nu, correlation based on h, dj and r, dj, r, the distance from stagnant point, was derived from experimental data. The Nusselt number distribution is independent of h, dj when h, dj is larger than 12 and r, dj is larger than 6. The PVC pipe jet with the length of 72 times diameters was adopted by Baughn to investigate fully developed impinging jet. Ray equals 23,000, h, dj equals 2 to 14. It is worth pointing out that the Nusselt number at the stagnation point reaches the maximum when h, dj is 2, and it presents a local minimum at r, dj equals 1.3. As the increase of r, dj, Nusselt number reaches a local maximum at r, dj equals 1.8 and then Nusselt number decreases monotonously. Cooper et al. Measured the mean velocity and the turbulence characteristics of the fully developed impinging jet for Ray equals 23,000 and 70,000. Their experiment rig was consistent with Baughn and Shimizu for comparison. The statistical parameters of turbulence in the stagnant zone of the impinging jet were reported by Nishino. Gears et al. Studied experimentally the impinging jet arrays. However, detailed comparison of these experimental results is much difficult due to that there are too many experimental conditions, specific dimensions and parameters affecting the impinging jet. LDA, laser Doppler anemometry, PIV, particle image velocimetry, LEAF, laser-induced fluorescence, liquid crystals, thermal tomography and numerical methods have been adopted to measure and analyze the flow and turbulence structure with different jets and jet-to-plate spacings of single impinging jet and jet arrays. The heat transfer enhancement mechanism of impinging jet is better revealed. However, it is still a big challenge to obtain optimal heat transfer performance of impinging jet in a specific circumstance. There are a great number of parameters that influence impinging jet performance including diameter and shape of the jet, spacing between the jet, arrangement, jet-to-plate spacing, morphology of target surface, jet angle, jet Reynolds number, turbulence intensity et al. Lots of work need to be carried out to reveal the heat transfer enhancement mechanism of impinging jet. Different morphology of target surface was carried out for optimal heat transfer performance, such as rib roughened surface, pin fin and other shapes. In 2000, Azad studied the heat transfer characteristics of impinging jet with cylindrical dimpled target surface experimentally. Re equals 4,850 18,300. D equals 0.5. The results showed that the Nusselt number of the dimpled cases and the corresponding smooth target surface cases are about the same. However, the dimpled surface provides higher heat transfer due to increased surface area when compared with smooth surface. In 2002, Eckert and Kontravitz firstly introduced spherical dimples to the target surface of impinging jet arrays. Re equals 4,800 minus 14,800. D equals 0.125, 0.25. H, dj equals 3 and D equals 0.5. Inline and staggered pattern between jet and dimple were adopted in their study. The results showed that the heat transfer coefficient of the dimpled target surface is lower than that of smooth target surface, which was explained as that the flow structure over dimples disturbs the impingement core. Recently in 2005, Kanokyarovijit and Martinez-Botas studied the heat transfer performance of jet impingement onto dimpled target surface. Re equals 11,500. D equals 0.29. H, dj equals 2 to 8. D equals 0.59. The effects of dimpled geometries, hemispherical and cusped elliptical, and crossflow schemes, maximum, intermediate and minimum, on heat transfer were examined. For minimum and intermediate crossflow schemes for H, dj equals 2, the heat transfer is reduced by 10% as the presence of dimples. For H, dj equals 4, the heat transfer of the impingement on dimples is almost the same as that of the smooth plate for minimum crossflow and improved by 10% for intermediate crossflow. Heat transfer is improved by 30 to 50% with H, dj equals 8 for intermediate crossflow and improved by 56 to 68% for maximum crossflow. Based on the above results, Kanokyarovijit pointed out that heat transfer enhancement is significant on dimpled target with large H, dj and high velocity overflow. Moreover, the pattern of dimple geometry, hemispherical and cusped elliptical, has little effect on the heat transfer performance. In the same year, Kanokyarovijit and Martinez-Botas conducted detailed research on the effect of main impingement parameters on the flow characteristics. Re equals 5,000 minus 11,500. H, dj equals 1 to 12. D equals 0.15, 0.25. When Re equals 11,500, H, dj equals 8, the heat transfer of dimpled target is enhanced by 50% compared with the smooth target. In cases of deep dimpled target and small H, dj, heat transfer decreases a little. While for large H, dj cases, heat transfer enhancement brought by deep dimple is also small. As to shallow dimpled cases, heat transfer is also increased for small H, dj condition. The result is the best when the impingement aims at the dimple center. Shallow dimpled target performs better than deep dimpled target on heat transfer performance. In 2006, Zhang et al. Investigated the parameter of Re, H, dj and E, sh, eccentricities, on the heat transfer performance of dimpled target of impinging jets. Re equals 5,000 minus 15,000. H, dj equals 0.5 to 11. E, sh equals 0 minus 0.5. D equals 0.3. D equals 0.29. In 2007, Zhang et al. Applied the impingement of dimple, protrusion arrays on the cooling process of electronic devices. Re equals 5,000 minus 15,000. In 2008, Kanokyarovijit and Martinez-Botas continued their previous works to investigate the effect of Re, H, dj, dj, and impingement position on the heat transfer and friction performance of dimpled arrays. Re equals 5,000 minus 11,500. H, dj equals 1 to 12. D equals 0.15 to 0.29. D equals 0.25 to 1.15. The results indicated that heat transfer enhancement increases with the increase of crossflow velocity. For shallow dimple, staggered arrangement of the impingement hole and dimple results in larger heat transfer rate, while deep dimpled target has opposite phenomenon. Shallow dimpled target has better performance than deep dimpled case. It is worth pointing out that the heat transfer ratio of shallow dimpled target reaches to 70% when H, dj equals 2. In 2009, Chang and Liu investigated the heat transfer performance of impingement on dimpled or protrusioned arrays and also considered the effect of leakage effect on the heat transfer performance. Turikov et al. Conducted experimental research on the flow and heat transfer performance of single impingement with dimpled target, Ray equals 12,000 to 58,000, H, dj equals 0 to 10, D, D equals 0 minus 0.5, dj, D equals 0.19. The results indicated that the flow characteristics of impingement on dimple are similar with that on the flat plate when D, D less than equals 0.13. When D, D greater than equals 0.26, large-scale vortex structure forms and heat transfer inside dimple is not as considerable as that on flat plate. Meanwhile, the fluid no longer contacts the target once it leaves the dimple cavity. Whether dimpled target could enhance the heat transfer process depends on the value of dj, d. Turikov pointed out that the mechanism of impingement on dimpled target need to be further investigated. In 2010, Xing and Weigand investigated the heat transfer and friction performance of arrays of impinging jets on dimpled targets. Ray equals 15,000 to 35,000, H, dj equals 3 to 5, D, D equals 0.15, dj, D equals 0.56. The results indicated that heat transfer is more considerable on lower crossflow velocity than that on higher crossflow velocity. Heat transfer increases with the increase of Reynolds number. Heat transfer enhancement is highest for small impingement distance, H, dj equals 3. Xing also pointed out that the mass flow rate is similar in all cases. Kanokyaruvidjit and Martinez-Botas summarized their previous works and obtained a correlation of Nusselt number with Ray, H, dj, D, D and dj, D. In the same year, they numerically investigated a laminar single impinging jet on dimpled target, H, dj equals 2 to 6, D, D equals 0.1 to 0.2, dj, D equals 0.25 to 1, adopting axisymmetric model and discussed the flow and heat transfer performance in detail. The results indicated that heat transfer decreases by 20% in this case compared with that of smooth target. By reviewing the literatures of impinging jet flow on dimpled or protrusion target, it can be concluded that the published literature mainly investigated the heat transfer and friction performance of impingement on dimple by experiments, and little results have published about the complicated flow structure. Especially, impinging jet on protrusion target is rarely studied. The present work focuses on the flow characteristics of single impinging jet on protrusion target by PIV and numerical simulation. A. Study on the flow structures. The vorticity of impinging jet flow on protrusion target surface at variable relative depth when dj, d equals 0.318 and Ray equals 5000 is obtained as shown in Figure 1. The coordinates z, r represent the axial and radial direction, respectively. The shaded areas indicate the location of the protrusion. High axial vorticity areas are considered as the position, transitional region, where jet core and surrounding fluids interact. The high vorticity is generated by the strong momentum and mass transfer at velocity discontinuity surfaces resulted by the large velocity gradient in radial direction. And the radial high vorticity is in the transitional region between the surrounding fluid and the wall jet. The PIV results have not captured the mini-separation flow in the transitional region between protrusion and target surface. The PIV particle medium would not have been distributed uniformly in the transitional region between protrusion and target surface. There would be less particle medium photographed by the PIV system. And so the mini-flow separation would not be observed in the PIV test. However, the CFD and experimental results reveal a close agreement in terms of vorticity. As protrusion relative depth increases, the turning angle between protrusion and target surface increases, which results in flow separation in this region. Moreover, the size of flow separation rises when protrusion relative depth rises. Furthermore, comparison of results between PIV experiment and CFD reveals that the flow structures on protrusion surface when Ray equals 10,000 and 23,000 are similar with that of Ray equals 5,000 at dj, d equals 0.318. The only difference is the vorticity magnitude and the size of flow separation in the transitional region between protrusion and target surface when Ray differs. In detail, higher Reynolds number can result in higher velocity and corresponding vorticity. Comparing the PIV and CFD results of different jet Reynolds numbers and protrusion relative depths when dj, d equals 0.5 and 1.045, it is shown that their basic flow patterns are similar to that of DJ, D equals 0.318. The only change is that the jet diameter gets bigger comparing with protrusion diameter, so the shear layer between the impinging jet and surrounding fluid moves outward radially. And the position of wall jet caused by the turning of impinging jet moves outward radially at the same time. The whole protrusion is located at the stagnation region when DJ, D equals 1.045, then the wall jet caused by impinging jet has not yet contacted with the protrusion surface. Through the summarization of CFD and PIV research in impingement flow on target with protrusion, the flow structure conceptual graph of impinging jet is obtained as shown in Figure 2. The pressure coefficient Cp is defined as Cp equals 2 multiplied PIPA, rho 0 U0 square. Here pi is the static pressure on target surface, Pa is the atmospheric pressure, Q0, U0 is the density and velocity at jet inlet, respectively. As for the stagnation areas, Tarikov et al. Describes the pressure coefficient distribution as dome-shaped distribution. The pressure coefficient distribution is indeed parabolic distribution via the analysis in this paper. The reasons are as follows. The impingement target near stagnation areas is relatively smooth. Martin has deduced a radial velocity distribution which is still approximately established today. Nu m equals CRR where CR is a constant parameter. Further deductions are as follows. Pi equals PO rho nu square, 2 equals PO rho multiplied square of CRR, 2 where PO is the total pressure. Substituting this formula into the definition of pressure coefficient we can get a parabolic distribution. Figure 3 shows the pressure coefficient distributions of target surface when DJ, D equals 0.318. According to the characteristics of pressure distribution and flow structure, the flow of single impingement on target with protrusion can be divided into 4 typical regions: stagnation region, wall jet region 1, protrusion edge region and wall jet region 2. Stagnation region exists where R, D between 0 and 0.2. The impinging flow undergoes an intense deflection and starts to accelerate quickly in the radial direction. Wall jet region 1 exists where R, D is between 0.2 and 0.45. Wall jet is formed in this region. The flow accelerates firstly and then decelerates. Region where R, D between 0.45 and 0.7 is called protrusion edge region. The flow continues to decelerate and the flow separation is induced because of the adverse pressure gradient. And then the wall jet begins to accelerate slowly after the reattachment of the separation flow. By the way, the flow separation has not formed when D equals 0.1 because the adverse pressure gradient is very small. Wall jet region 2 exists in areas where R, D is above 0.7. The pressure coefficient distribution of target surface is not sensitive to jet Reynolds number and protrusion relative depth as shown in the figure. So the conclusion is confirmed that whole flow structure is single and it varies slightly with jet Reynolds number and protrusion relative depth. However, impinging jet flow structure is a little bit different when jet Reynolds number and protrusion relative depth change. The impact of jet Reynolds number change mainly concentrates in the area of protrusion edge region. For instance, pressure increment along protrusion edge region increases as jet Reynolds number increases due to the larger geometrical catastrophe in the transitional region between protrusion edge and target surface. Flow accelerates faster near stagnant region with the increase of protrusion relative depth and spherical curvature, which induces larger pressure increment near wall jet region 1 and protrusion edge region. Furthermore, flow separation is formed in the local region near protrusion. As shown in Figure 4 and Figure 5, the variation of pressure coefficient distributions with jet Reynolds number and protrusion relative depth when DJ, D equals 0.5 and 1.045 is almost same with that of DJ, D equals 0.318. And the only difference is that wall jet stagnation region gradually gets larger comparing with the protrusion diameter as impinging jet diameter increases. Particularly, impinging jet diameter is almost equal to protrusion diameter when DJ, D equals 1.045 and the interacting region of protrusion is just located in stagnation region of impinging jet, then impinging jet continues to accelerate. After passing through protrusion edge, a local peak of pressure coefficient is observed at protrusion edge region in all cases. Velocity and pressure field is shown in Figure 6 when DJ, D equals 0.318, d equals 0.3 and Re equals 23,000 to explore the factors that result in the local high pressure peak. In the figure, the arrow indicates the direction of the velocity. The velocity decreases firstly and then increases in region 1. The flow direction changes at the same time. Velocity distribution in region 2 is similar to that in region 1. So the flow in region 2 is regarded as impinging jet with inclined angle, which is called secondary impinging jet in the present study. The local high pressure coefficient is caused by the secondary impinging jet. The wall jet developed in region 1 impinges onto the target wall and secondary impinging jet is formed. The velocity of impinging jet decreases because of interaction with wall, resulting in the increase of static pressure. Besides, flow direction changes in this region, and pressure gradient gets bigger by the centrifugal force resulting from streamlines bending. Thus it is concluded that secondary impinging jet formed at protrusion edge region causes the local high pressure peak. According to the analysis above, the flow structure conceptual graph of the impinging jet towards protrusion target surface need to be improved and the secondary impinging jet should be added in the figure. The accurate conceptual graph is drawn as figure 7. Based on figure 2, blue arrows are added in figure 7 to represent secondary impinging jet and the angle B stands for the turning angle. Local Nusselt number distributions. Local Nusselt number distributions on protrusion target surface when d equals 0.318 are shown in figure 1. Nusselt number distributions on smooth target surface are also presented for comparison. 3 vertical lines in figure 1 correspond to that in figure 2, which divide flow field into 4 regions. Local Nusselt number increases with the increase of jet Reynolds number on the whole. In the stagnation region, local Nusselt number decreases radially outward and the decreasing rate of local Nusselt number gets faster as jet Reynolds number increases. Local Nusselt number increases as protrusion relative depth increases at a constant jet Reynolds number. This is because that the distance between protrusion dome and impinging jet nozzle gets smaller when the protrusion relative depth increases. So the heat transfer is improved significantly. The difference of local Nusselt numbers between different protrusion relative depths decreases radially outward. In wall jet region 1, local Nusselt number decreases as protrusion relative depth increases at a fixed jet Reynolds number. Local Nusselt number difference between different protrusion relative depths gets larger radially outward. Distributions of local Nusselt number with the change of protrusion relative depth in wall jet region 1 is just the opposite of the stagnation region. This is due to that the wall jet in wall jet region 1 accelerates firstly and then develops with pressure increment. The pressure increment increases as the protrusion relative depth increases, which results in thicker boundary layer. And so the heat transfer is deteriorated. In protrusion edge region, local Nusselt number drops rapidly firstly and then goes up and drops again for each case. The local Nusselt number peak corresponds to the stagnation region of secondary impinging jet. However, the distributions of local Nusselt number in protrusion edge region show different features for different Reynolds numbers and protrusion relative depths. 4. The cases of Re equals 5,000, 10,000 and delta D equals 0.1, 0.2, local Nusselt number distributions after passing through protrusion edge region show the same with that of the smooth target surface, but local Nusselt number for delta D equals 0.3 and Re equals 5,000, 10,000 after passing through the protrusion edge region is noticeably lower than that of the smooth target surface. Local Nusselt number in protrusion edge region at Re equals 23,000 and delta D equals 0.1 is rise to the same level as that of smooth target surface, and then keep the similar value as that of smooth target surface as flow develops outward radially. However, the maximum local Nusselt number in protrusion edge region at Re equals 23,000 and delta D equals 0.2, 0.3 is much larger than that of smooth target surface, then local Nusselt number decreases again after up to the maximum and reaches the same level as that of smooth target surface in wall jet region 2. As protrusion relative depth increases, the turning angle B gets bigger, which leads to larger scale of flow separation and larger inclination angle of secondary impinging jet. These two factors have opposite effect on the heat transfer of the protrusion edge region. To explain the local Nusselt number distributions in the protrusion edge region, the velocity distributions along z direction in the peripheral region of local maximum Nusselt number are shown in figure 3 when Re equals 10,000. The boundary layer thicknesses when delta D equals 0.1 and 0.2 are almost the same comparing with that when delta D equals 0.3. As analyzed before, a larger scale of flow separation occurs in the transitional region at protrusion edge region when delta D equals 0.3, which leads to more flow loss and thicker boundary layer. Although the increase of the inclination angle of secondary impinging jet contributes to heat transfer improvement, the flow loss and the energy decrease of impinging jet cause substantial deterioration in heat transfer. The inclination angle of secondary impinging jet is the dominant form of heat transfer when Re equals 23,000, delta D equals 0.2 and 0.3. Thus local Nusselt number peaks in protrusion edge region at delta D equals 0.2 and 0.3 are larger than that of other cases. Figures 4 and 5 presents local Nusselt number distributions when DJ D equals 0.5 and 1.045, respectively. The effect of protrusion on local Nusselt number distributions is similar to that of case DJ D equals 0.318. However, there exist some slight differences as follows. Firstly, Nusselt numbers in all cases are almost the same with that on smooth target surface after passing through protrusion edge region. Secondly, the local maximum Nusselt number due to secondary impinging jet is higher than that on the same place of smooth target surface when DJ D equals 0.5, D equals 0.2, 0.3 and Re equals 10,000, and when DJ D equals 1.045, D equals 0.2 and Re equals 23,000. The local maximum Nusselt number due to secondary impinging flow shows the same level with that on the same place of smooth target surface. Stagnation Nusselt number. Figure 1 shows the stagnation Nusselt number distributions of impinging jet on protrusion target surface with the change of jet Reynolds number. The stagnation Nusselt number distributions on smooth target surface by literature 26, 29 are introduced in the present numerical study for comparisons. The correlative expression are given by Tarikov et al. Nu 0 equals 1.24 pr to the power of 0.33 Re to the power of 0.5 L by dj to the power of minus 0.11. While the expression by Li and Li Nu 0 equals 0.433 Re to the power of 0.565 L by dj to the power of 0.0384. Tarikov and Li adopted different experimental details to obtain the correlative expressions. A certain deviation exists in their expressions. Based on the present study, a correlative expression of stagnation Nusselt number between Nu 0 and D, Re, dj, D is given below. Nu 0 equals A0 Re to the power of A dj by D to the power of beta delta by D to the power of gamma, where A0 equals 1.4069, alpha equals 0.5116, beta equals 0.1347, gamma equals 0.1388. The mean square deviation is 2.72%. The variation of stagnation Nusselt number is obtained through the coefficients in the above correlative equation and the figure. Stagnation Nusselt number is higher with larger protrusion relative depth, jet to protrusion diameter ratio and jet Reynolds number. Furthermore, stagnation Nusselt number on target surface with protrusion is higher than that on smooth target surface. The distance between protrusion dome and impinging jet nozzle gets smaller when the protrusion relative depth increases, so the heat transfer in the stagnation is improved significantly. Average Nusselt number of protrusion. The averaged heat transfer characteristics of impingement target surface are more concerned. The averaged Nusselt number. Nu average is defined by Nu average equals sigma nu I dsi by sigma dsi multiplied by sigma dsi by sigma dpi, where nu I is the local Nusselt number of every element on the protrusion surface, dsi and dpi are the protrusion element surface area and corresponding projected surface area, respectively. This definition of average Nusselt number takes the heat flux brought by additional area of sphere comparing with flat surface into account. For more convenient comparisons, the average Nusselt number of impingement on flat plate with comparable areas is given. Figure 2 presents average Nusselt number distribution on the protrusion surface with the change of jet Reynolds number. Average Nusselt number for smooth target surface with corresponding areas is also given for comparison. Based on the present numerical results, a correlative expression of average Nusselt number on protrusion surface nu average between delta by d, Re, dj by d is obtained. Nu average equals A0 Rj to the power of alpha dp by d to the power of beta delta by d to the power of gamma. Among them A0 equals 1.5325, alpha equals 0.4864, beta equals 0.2873, gamma equals 0.1335, the mean square deviation is 4.78%. The variation of average Nusselt number on protrusion surface is obtained and it is summarized as below. The variation of average Nusselt number on protrusion surface is the same with that for stagnation Nusselt number. In detail, Nusselt number is higher with larger protrusion relative depth, jet to protrusion diameter ratio and jet Reynolds number. However, it is worth pointing out that average Nusselt number on protrusion, when dj by d equals 0.318, 0.5 and delta by d equals 0.1 has slight difference with that for corresponding smooth target surface. The average Nusselt number of protrusion except the above case is higher than that of smooth target surface. For further deduction, the overall improvement of heat transfer for most cases is obtained by the heat transfer enhancement in stagnation region and the increase of protrusion sphere area. Conclusions. The flow characteristics of a single jet impinging on a protrusion surface were investigated using PIV and numerical simulations, and the heat transfer characteristics were explored on the basis of the numerical results when dj by d equals 0.318, 0.5, 1.045. Delta by d equals 0.1, 0.2, 0.3 and Re equals 5,000, 10,000, 23,000 for the first time. The detailed conclusions are drawn as follows. Flow structures of impinging jet on protrusion target surface are not sensitive to protrusion relative depth and impinging jet Reynolds number. The jet turns its flow direction as it impinges onto the protrusion. Then the flow separation occurs when flow passes through protrusion edge region and at the same time secondary impinging jet forms. The wall jet continues to develop along the radial direction after apart from the edge of the protrusion. According to the characteristics of pressure coefficient distribution when dj by d equals 0.318, the flow of single jet impingement on the protrusion target can be divided radially into 4 different regions: stagnation region, wall jet region 1, protrusion edge region, and wall jet region 2. Wall jet region 1 gets smaller with the increase of dj by d. The protrusion is covered by impinging jet stagnation region completely when dj by d equals 1.045. The local Nusselt number on the protrusion surface is higher in the comparison with smooth surface on the whole, and the local Nusselt number increases with the protrusion relative depth. However, local Nusselt number decreases with the increase of protrusion relative depth when the wall jet passes into protrusion edge region. Local Nusselt number drops firstly and then increases. Drops again in protrusion edge region, so the peak value emerges, which can be explained clearly by the secondary impinging jet concept proposed in the present. The local Nusselt number recovers to the same level with that of smooth target surface after passing through protrusion edge region, and decreases gradually as flow develops. Based on the numerical results, the correlative expression of stagnation Nusselt number between nu0 and delta by d, Re, dj by d is obtained. Stagnation Nusselt number increases with the increases of protrusion relative depth and jet Reynolds number, and stagnation Nusselt number on protrusion target surface is larger than that of smooth target surface. Based on the numerical results, the correlative expression of average Nusselt number between nu0 and delta by d, Re and dj by d is obtained. It takes both the decrease of the local Nusselt number after arranging the protrusion and the increase of the heat exchange area into account. The average Nusselt number increases with the increase of protrusion relative depth and jet Reynolds number. The overall improvement of heat transfer for most cases is obtained by the heat transfer enhancement in stagnation region and the increase of protrusion sphere area.